Hello everybody, welcome back to another NumPy video. The focus of this video is going to be something called the axis keyword argument, and motivating this discussion is the question, well, if I roll four distinct six-sided dice, what is the probability that the largest number that shows up among the four dice is the number 5? So again, we're answering another probability question, and we'll see this axis keyword come up during our discussion of it. So I already have NumPy imported, so what I'm going to do is define the default random number generator. So I'm going to say RNG equals np.random.default_RNG. And then what I'm going to do is, now let's imagine, how do we set up this experiment? So I want to roll 4 distinct six-sided dice. So what I'm going to do is I'm going to call my array ARR equals RNG.integers, or maybe first, before we even define it, let's think about this. We have RNG.integers. What are the values that show up on a six-sided die? Well, I could go from 1 to 6 inclusive. So because I want to include 6, I go up to 7 here. And if I want to roll 4 dice, I can say size equal 4. So notice here, this represents the first roll, the second roll, the third, and the fourth. So we can see here the maximum that appears is 6. If I run it again, the maximum that appears is 5. So we can imagine every time I run this RNG.integers, this represents me rolling 4 distinct six-sided dice. And then I can look here and see, well, the largest number that shows up is a 6. So we're wondering, what's the probability that I roll these 4 dice and the largest that shows up is a 5? So let's start by modeling the experiment like we normally would. I'm going to start with a relatively small number of experiments and then we'll increase it. So let's say experiments is equal to 10. S stands for success. I'm going to initialize it to 0. And let's start by computing this using a for loop. So I'm going to say for I in range of experiments. Now what I want to do is call RNG.integers 1 to 7, size equals 4. And remember, what are we counting as success? Well, we're counting a success as the maximum number showing up being a 5. So what I want to do is I'm going to take the maximum of this. But another thing to keep in mind, oops, and look, this parenthesis is red, so it means I'm missing one here. So regular max could work, but there's also np.max, and as we've seen in previous videos, the NumPy max is going to be more optimized, so this is going to be a lot faster in theory than just regular max. Good, and we want to see, well, is the max equal to 5? So if this is true, what do we want? Well, S is equal to S plus 1. Great. So now let's compute the expected, or our estimated probability. So number of successes divided by number of experiments. And notice here we get 0.3, so 30%. So one thing about this for loop is it's very slow. So I'm going to time the experiment now. We're going to increase it to 1 million experiments. But it's so slow, in fact, that instead of using time it like we've done in other videos, I'm going to use just time. And what this is going to do in here, so I want, instead of 10, 10 to the 6. And as we're waiting for this to run, I want to remind you what this, if I used to time it. So let's find an example of where I've used it in a previous video. So notice here, it tells me how many runs. So it's done 7 runs, 1 loop each, so it ran it 7 times. This one did 7 runs, 100 loops each, so 700 times. And that's time it, versus just time is going to run it just once. So we can see here, it took 18.2 seconds for this to run, which, considering that this is only 1 million experiments, that's very slow. And here, so we got 0.28. So this is the for loop way. What else do I want to say about this? I'm going to show you a different way now that's using features from NumPy. It's still going to be slower than we'd like, but the advantage is it's more flexible. It can work with a larger variety of situations. So maybe let's move into the second method that I want to show you. So once again, I'm going to say, let's start with experiments equal to 10. Then what I'm going to do is let's let RNG.integers. I want this to go from 1 to 7, and I still want the size. So I still want to have 4 dice rolls, but now what I can imagine is I want to have each row of an array corresponding to an experiment. So instead of 10 here, I can do experiments. And let's take a look at what this looks like. So notice here, the first row represents the first experiment. So I roll 4 dice, and the maximum that appears here is 6. Here's the second experiment. I roll 4 dice, the maximum that appears is 6. Let's see if we can find one where the maximum is 5. So here, the last one, that's one where the max is 5. And it looks like that's the only one. I can run it again and get different numbers. So like this, let's see. Here's one where the maximum that appears is 5. Here's another one where the maximum that appears is 5. So how about I'm going to call ARR equals RNG.integers 1 to 7, size equals number of experiments, comma 4. So there's ARR. I'm going to print it. Keep in mind, every time we run that block of code, the numbers are going to change just because we're calling RNG.integers. So that's kind of what we're looking at. One thing I want to kind of show you now is what if I tried np.max of ARR? So this isn't going to be quite what we expect. So notice if I run it, it gives me just one number and it's saying, well, the maximum is 6. So what's going on here is it's not taking the maximum along the rows, it's taking the maximum in the entire array. So notice the maximum that appears is 6, so that's what it's returning. So the way we're going to counteract this is we're going to use something called np.apply along axis. So let's take a look at help for that. So I'll say help np.apply underscore along underscore axis. And let's take a look here at the function signature. So it's saying the first thing I pass as an argument is the function. So this is the function I want to apply. So in this case, it'll be np.max. Then this third thing here, it's telling me, well, ARR, that tells me, well, what's the array that I want to use? And the point of this video and what I want to focus on is this axis argument. So axis argument, we're going to have a video talking about it in more depth, but you can imagine it as saying, what direction do I want to apply the function along? So if we look up here at ARR, I could take the maximum in this horizontal direction. So you can imagine is we're fixing a row and varying the columns. So this is called axis 1. It's also known as the columns axis. I like to think of it as like a horizontal direction that we're moving along. Versus if I were to move vertically, so I'm fixing a column and varying the rows. So this is axis 0, also called the rows axis. So let's see an example of this in action now. So I'm going to do, let's see, np dot apply underscore along underscore axis. The function I want to apply is np.max. Like I said, axis, I want this to be equal to 1. And again, the reason for it is I'm moving in this horizontal direction, so that corresponds to axis 1. And then ARR is just going to be what we called ARR above. So now let's take a look. So notice the maximum in this first row was 3. That's where we get 3. The maximum in the second row was 6. That's where we get 6. In the third row was also 6. Then a maximum of 4, 3, 6, 6, 5, 5, and 3. So this is an example of how we could get it to compute the maximum along the rows. Just as an example, notice if I change this to axis equals 0 instead, can you predict what will happen? So remember I said axis 1 is moving in this horizontal left and right direction. Axis 1 is going to move up and down. So we're going to fix a column and vary the rows. So let's do axis equals 0. And notice here what it's doing is it's looking at this entire first column and we're taking the maximum. So I have 2, 1, 4, 3, 2, 4, 3, 3, 5, 1. 6 never appears. 5 is the largest number that appears. In the second column, there's a 6, so that's the largest. In the third column, the largest that appears is a 5. And in the last column, the largest that appears is a 6. So here's 2 examples. For our experiment, remember each row represents an experiment. So we're going to want to use np.apply along axis for axis equals 1. So now let's actually see how we could do the probability computation. So what I'm going to do is, again, let's let our number of experiments be 10 just to start. I'm going to say ARR equals RNG.integers 1, 7. Our size is going to be number of experiments. So let's do experiments, comma 4. And then, okay, so remember if I do np.apply along axis, we have np.max, and we have axis equals 1. We want our array to be array. And remember now we're asking, is the maximum 5? So what we should do is ask, is this equal to 5? So notice we have false, true, true, and then a bunch of Boolean values. So they're all Boolean values. So one way that we could compute the probabilities, remember we want to compute number of successes divided by number of experiments. So notice there's 10 experiments here, and false is 0, true is 1. So if we sum up all of these values and divide by 10, that will give me the probability estimate. So all of that to say is if I take the mean of this, I can get my probability estimate. So here we only did it with 10 experiments. Let's now try to kick it up to 10 to the power of 6. So everybody editing me here, I realized in the original recording of this video I had used the wrong Jupyter Magic for timing, and it was giving me some results that I was not expecting. So at this point in the video, we had just finished kind of the setup for this NP apply along axis function with 10 experiments, and we were going to kick it up to 1,000,000 experiments and try timing it. So I'm just going to re-record that portion really quick so that the numbers are closer to what I expected. So I'm going to copy this, make a new cell, and instead of having 10 experiments, I'm going to have 1,000,000. And now let's use the Jupyter Magic time, and we'll see how long it takes. So it says here, it took 5.92 seconds. So if you remember when we first did this problem with the for loop, it took us 18.2 seconds. So that was really slow considering that it's only 1,000,000 experiments. So this is faster, sure, but it's still pretty slow, all things considered, right? It's still about 6 seconds. And you might be wondering kind of why is that the case, especially because NumPy is supposed to be optimized. And kind of what goes wrong here is that np.apply along axis is very general. So it's not optimized for this particular type of computation. So remember, we could really put any function that we want here. So it's because it's so flexible, it's just not optimized. That explains why it's so slow. So in the next part of the video, we're going to talk about a method that's way faster. And I'm going to quickly re-record that computation time as well, just because I had originally used the wrong magic. I want number of experiments and the array to be, oops, didn't mean to do that. Let's see, I want to copy paste these 2 lines. So I'm going to start with 10 experiments, define ARR in the same way. Now, one thing I could do ARR.max. And one thing I want you to do is predict what's going to happen here. So notice here, it's still just returning a single value 6. And that's because it's the same issue that was happening earlier when we did np.max. It's taking the maximum of every element in the array. So maximum, it still has an axis argument. So for instance, if I call help on, let's see, ARR.max. So notice here, it has an axis argument. So I could pass an axis argument here. So let's try it again. But now remember, we wanted to work along axis equals 1. And we can see here. So notice we did 10 experiments. So I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 results. So the maximum here was 5, then it was 6, 5, and then we can keep going on. So again, what would I do if I wanted to get the probability estimate? Well, I could take the average again. So I could do dot mean. And we can see here 5.5. Now keep in mind, it's not going to be exactly the same as this computation here, in case you're trying to compare them. And that's just because whenever I call this rng.integers, this is creating a new array. So now let's actually try to do the computation, but with more experiments. So let's see, now I'm going to have 10 to the 6 experiments. And let's see, we'll do time to see how long it takes. Again, still editing me here. So same issue as before with the wrong Jupyter Magic. So here, we're now using this ARR.max along axis equals 1. And we're just kicking up the experiments to 10 to the 6. And I want to use time to see how long it takes. So we can see here it took 60.5 milliseconds. So a little under 1/10 of a second. That's very fast, especially compared to the 5 seconds that it took us earlier for another kind of NumPy function. Okay, I'm gonna head out and pass it back to the original video. Maybe one more thing I want to say. So notice this mean here. If you were to call help on mean, we could also apply an access argument, but keep in mind when I just do arr.max, so let me show you. So notice this is a one-dimensional NumPy array. So there's just one axis dimension, right? It's just the 0, 1. So if I do .mean axis equals 0, which is the default, this just returns the average. But if I do axis equals 1, it's going to throw an error just because there's only one dimension. So there's no second dimension for it to kind of concatenate or take the mean along. So I think this is a good place to stop the video. Thank you for watching, and I will see you in the next one.